In this video, I have discussed Chapter 9 of Class 9 NCERT Science textbook named Force and Laws of Motion. In the beginning part of the video, I have discussed the complete concept of the chapter, which consists of definitions, formula derivations, laws, and towards the end of the video, I have discussed the textbook exercise questions followed by solutions. I hope this video is useful for Class 9 students. Now let's begin the chapter's discussion. The chapter, second chapter of physics, but in the textbook it is chapter 9, Force and Laws of Motion. So I have kept the complete chapter theory in form of written notes, and I felt this is the best way of explaining it. This notes I'll put in the link in form of PDF so that you can take the hard copies, and before exam you can have a quick revision of this chapter, Force and Laws of Motion. So first we'll begin with a definition of force. How do you define force? Sometimes that 1 mark question comes, define force. So force is a push or a pull that brings about change in the state of rest, uniform motion, direction, shape or size of an object. So force is actually kind of push. Push means we talk about a direction, that means this much amount in a particular direction. Pull means this much quantity in a other or particular direction. So force is a push or pull that brings about change in the state of rest, uniform motion, direction, shape or size of an object. So clearly from this word push and pull, it is understood that force is a vector quantity. It has got magnitude as well as direction. Force is measured in terms of Newton, which is its SI unit. So when you write Newton, we write capital N. And if you happen to write small letter n, keep this in bracket. The lower unit of force, that is CGS unit of force, is dynes, D-Y-N-E. CGS is centimeter gram second. Next, we classify force. How do you classify force? In the lower classes, we were classifying force as contact force and non-contact force. Contact forces are forces like with contact we can apply that force, like muscular force, those are contact force. Non-contact forces are gravitational force or magnetic force or electrostatic force, where the object where the push or pull is applied, it is not directly in contact. So that is one classification. So we can classify force as contact force and non-contact force, but in this chapter force is classified as balanced forces and unbalanced forces. So first, what is the meaning of balanced forces? So you just assume this diagram, but before diagram and the theory that I wrote here, just understand what is the meaning of balanced forces. That means when many forces are there on a body, are applied on a body, and all of them balance each other. That means none of the forces are dominant. So those forces are called balanced forces. So now technically when we write a definition, like when we write definition for marks purpose, this is what we do. So this is the horizontal surface on which an object of certain mass m is placed. This is acted upon by force of gravity. So force of gravity constitutes the weight of the body. Let's call this as F1, and this is called action. And for every action there is an equal and opposite reaction. So inward weight of the body due to gravity, perfectly opposite direction, same magnitude, normal reaction. And say this object is pulled in a particular direction by some applied force, we call applied force as F3. Then whenever we pull or push an object, between the object and the surface and surface of contact, there will be a force of friction. So the force of friction appears or comes into play in the opposite direction, which we call it as F4. Now coming to the definition of balanced forces, when a number of forces, means when many forces act on a body such that the resultant other technical terms or terms are net or total. When a number of forces act on a body such that resultant of all forces acting on it is a 0. That means when so many forces are acting on a body, but sum total of all the forces acting on the body turns 0. So if resultant is 0, then the body is said to be under balanced forces. So this is the case where force of gravity and normal reaction. So the inward force and normal reaction, these two are equal in magnitude but opposite in direction. So in a way they cancel each other. Similarly, applied force, when it is equal to opposite force of friction, because they are in opposite direction, and if applied force and force of friction are in same magnitude, they also cancel each other. So ultimately net force acting on this object is 0. So this object is under balanced forces. Then any object that is under balanced forces, what happens to it? So under balanced forces, an object is at rest. Under balanced forces, if an object is at rest, it remains at rest. And if an object is in uniform motion, it continues to move at the same speed. That means which object is in which prior condition, post also it remains in the same condition under balanced forces. Mathematically, when you sum up all the forces, you have to just tell that force weight of the body is equal to normal reaction but opposite direction. Then applied force is equal to force of friction but opposite direction. Ultimately all of them cancel each other and 0. Then we are supposed to give examples of objects in balanced forces. So objects under uniform circular motion are best examples of objects which are under balanced forces. See, if object is under uniform circular motion, means we take a stone and tie a string and we try to turn around our hand, then every moment we are pulling the object towards the center of the circular path in which that stone is turning. Then the inward force with which we are pulling the stone towards our hand is the centripetal force. Then automatically the opposite direction, same magnitude force comes into play. The opposite, the outward force that comes into play is called the centrifugal force. So the inward centripetal, outward centrifugal force balance each other. So every object that is in uniform circular motion is under balanced forces. So I wrote an example here. Objects in uniform circular motion are under balanced forces of inward centripetal force and outward centrifugal force. One more example we can take up. Planets orbiting sun are under balanced forces. Now the second classification of force, the unbalanced forces. When do we say that objects are under unbalanced forces? That means you can make out that the object is under unbalanced force. That means definitely there is some force that is a dominant. So this is how we define. When a number of forces act on a body such that the resultant of all forces acting on it is not 0, then the body or the object is acted upon by unbalanced forces. When we want to explain unbalanced forces, we better show the inclined plane. So on the inclined plane, an object is placed of certain mass, and we can make out that there is force of gravity, there is contact force, there is normal reaction, then this is also kind of force of gravity in this direction, and then force of friction. So many forces, out of them few are labeled here, are acting on this object, and definitely all the forces are not cancelling each other. So the mathematical expression for unbalanced forces is the algebraic sum of all the forces acting on the body is not equal to 0. In that case, the body is under unbalanced forces. Then what happens if an object is under unbalanced forces? That's a 1-mark question, sometimes it appears. Under unbalanced forces, an object either starts accelerating or starts decelerating, but it is no more in the same state as it was before when it was not under unbalanced forces. So when the moment the body comes under unbalanced forces, the body either starts accelerating or decelerating. Then let's give some examples of objects which are under unbalanced forces. Every rolling object is under unbalanced forces. The best example can be an oscillating pendulum. When it undergoes a damped oscillation, under that is an example of unbalanced force. Means under the gravity of earth, say we have a rigid support and then there is a pendulum. We take this pendulum to the extreme position and then some amplitude, okay, and once you release it, the pendulum goes to the other end and up to the same amplitude for sure. But after some time, this oscillation starts damping and ultimately the pendulum stops oscillating under many forces, gravity, air, friction, many of them. And in that case, oscillation of a simple pendulum can be the best example for objects under unbalanced forces. I wrote one more example. Any rolling or sliding object remains under unbalanced forces. So rolling and sliding objects are also good examples of unbalanced forces. This chapter is about force and laws of motion. Laws of motion were first given by Galileo Galilei, and next it was given by Newton. This chapter, laws of motion, we will learn is about Newton's laws of motion. Galileo in fact gave two laws of motion. Galileo's first law is made into Newton's first law and second law, and Galileo's second law is actually Newton's third law. Now this chapter is about Newton's laws of motion. So Newton gave three laws of motion. The first law, Newton's first law of motion, is otherwise known as the law of inertia. As we move forward, we will know about inertia. Newton's first law statement we should know. So it states that every body in this universe remains in the state of rest or of uniform motion unless or until, or you can say unless and until, it is acted upon by some external force. Its meaning is, if an object is at rest, it remains at rest. And if an object is in uniform motion, it continues to move with the same speed. How long? Unless and until that object is acted upon by some external force. That means if an object is at rest, it will definitely stay at rest. It will only move when some external force is applied to it. So that is what Newton's first law of motion states. So mathematically, if F is equal to 0, its meaning is when no force is applied, the initial state of the body and final state of the body are same. That's Newton's first law of motion. So Newton's first law of motion states that every body in this universe remains in the state of rest or of uniform motion unless and until it is acted upon by some external force. That means if no force is applied, the previous condition of the body and final condition of the body are always the same. So Newton's first law of motion is otherwise known as law of inertia. Now what is the meaning of inertia? Inertia is actually an inherent property of every body, every object. So inertia is an inherent property of the body, or the inability of a body. Actually it is the inherent property. And what is that inherent or inbuilt property? That inherent or inbuilt property is a kind of inability. So inertia is inability. Which kind or what kind of inability? It is the inability of a body to change itself, its state of rest, uniform motion or direction. It's very simple meaning. Inertia is the inability of a body to change itself, its state of rest. Means if an object is at rest, just like this pen, if this object is at rest, this object has the inability to change itself, its state of rest. Means this pen of its own or on its own can't start walking away. Okay, so that is its inability, and that is called inertia. Or if we have, like in this room right now, there is a fan that is turning. So that fan has the inability or inertia. What kind of inertia? Inertia of motion. That means on its own it can't stop. I have to get up and switch off, and then slowly it will stop. So inertia is that. So inertia is the inability of a body to change itself, its state of rest, uniform motion or a direction. So there are three types of inertia: inertia of rest, inertia of motion, inertia of direction. So sometimes we will be asked to define inertia of rest, inertia of motion and inertia of direction. So very quickly I'll give definition for inertia of rest. Inertia of rest is the inability of a body to change itself, its state of rest. Inertia of motion is the inability of a body to change itself, its speed. That means if an object is traveling with say 40 kilometers per hour speed, unless you accelerate the body or decelerate the body, its speed is not going to either increase or decrease. Inertia of direction is the inability of a body to change itself its direction. Like if I roll a ball on a straight road and there a turning comes, the ball on its own will not take the turn. So that is the inability of that ball to change its direction. So those are inertia. So just remember that inertia is an inbuilt property of a body which resists the change. Okay. So inertia is actually a property, and properties are not physical quantities that they can be measured, but inertia can be measured because inertia depends upon mass of a body. So sometimes this 1 mark question appears in the exam. They say, what is the measure of inertia? Means how do you measure inertia? Inertia is measured in terms of mass of the body. Its meaning is if mass of a body, if mass is more, inertia is more. That means huge bodies have more inability, smaller bodies has less inability. Like a tennis ball is very free to move, but a shot put is difficult to move. So more mass means more inertia, means more inability. So inertia can be measured, so it can be treated like a physical quantity. So standard international unit of inertia is kilogram. In that case, what is CGS unit of inertia? Think. Now I have written the 3 types of inertia and quoted some examples. Inertia of rest I already defined. Just go back in the video once, see that definition, listen to that definition once again, or you can read it also. Now how to give an example of inertia of rest. Passengers in a bus experience a backward jerk when the bus starts suddenly. Why so? That is due to inertia of rest. You understand, when a bus is at rest and passengers are sitting or standing and the bus starts suddenly, when the bus starts suddenly, the upper part of the body experiences a backward jerk. Why? Because the lower part of the body is in contact with the bus, so it experiences a direct force. So force is applied, change will be seen, but the upper part of the body, no force is applied, so it has the inability to change its previous state, and previously it was at rest, so it want to be at rest. Where? At the same location where it was before the bus started. In that process, the upper part of the body experiences a backward jerk when the bus starts suddenly. So like that. So there can be tons and tons of examples, like leaves, flowers, fruits of a tree fall or get detached when the branches are shaken vigorously. Why? Because direct force is applied to the branch. So branch moves forward or backward, but the leaves, flowers, fruits tend to stay at the same location. So that's an example of inertia of rest. Dust can be separated from carpet by beating the carpet, because when we hit the carpet experiences a force, but the dust particles would like to remain at the same position, and since they stay back and they don't have a support system, they fall down. So like that. Those are the examples of inertia of rest. Then coming to inertia of motion. So the definition already I said. Example, passengers in a moving bus experience a forward jerk when the bus stops suddenly. Why this happens? This happens due to inertia of motion. Now think in the same lines. When the bus is moving, so the bus was traveling and it had some speed, and all of a sudden the bus comes to rest. In that case, the lower part of the body all of a sudden comes to rest, but the upper part of the body is in motion. It has the same speed as the bus had before stopping. So the upper part of the body continues to be in motion, and in that process the lower part of the body comes to rest and the upper part of the body experiences a forward jerk. That happens due to inertia of motion. So the best example, sometimes they say that while jumping, one should not do it, but I'm just saying, while jumping out of a moving bus or a train, one should jog, being in the bus or the train, and jogging only, we have to step out into the platform. In that way we can overcome the chances of falling flat on the platform. That's an example. Or one more example, or few more examples, that athletes in a track and field event don't stop all of a sudden at the finishing line. They leap few steps forward. because if they stop all of a sudden, then there are more chances that the athletes fall flat due to inertia of motion. Then the third inertia of direction, passengers in a moving vehicle are thrown away from the center of curved path when the vehicle takes a turn, and that happens due to inertia of direction. So you can make out. So these are the types of inertia and examples. So that was Newton's first law and law of inertia, and inertia and types of inertia. Now before going to Newton's second law of motion, we should know about momentum. Momentum is denoted by the letter P. It can be capital letter P or small letter p, and it is a vector quantity. So since it is a vector quantity, you can put an arrow above and put under modulus. So momentum is represented like this. So what is momentum? Momentum is actually the quantity of motion possessed by a body. What is the meaning of this? That means any object which is in motion, if we have to apply lot of force to stop it, then that object has more momentum. And if less force is applied to stop a moving object, then that moving object has a less momentum. In that way you should understand. So what is momentum? Momentum is the quantity of motion possessed by a body. So that's what I wrote here. So how do we define it? It is the product of mass and linear velocity. Mathematically, momentum is mass into linear velocity. Velocity is a vector quantity, so it is written in this form. So momentum is mass into linear velocity. In short, we can just know that momentum is mass into velocity. Mass into initial velocity is initial momentum. Mass into final velocity is final momentum. So SI, Standard International Unit of Momentum, is kilogram meter per second. And CGS unit, centimeter gram second, unit of momentum is gram centimeter per second. Momentum is a vector quantity. Now we will come to Newton's second law of motion. So before going to Newton's second law of motion, let's see what's there in the textbook. So here these are the pictures of what happens when force is applied to a body. And this is a picture where we understand balanced forces and unbalanced forces. And then this is a picture where if forces are applied in the, say, in one direction, so this is the direction of applied force, and this is the force of friction that comes between this object, these two. So the object will move in which the forces are dominant, like say forward direction force is 100 Newton and backward direction force is a 20 Newton, then the net force is 100 minus 20, that is 80 Newton. So that's what is to be understood. But if force is applied in opposite direction, then the net force is the difference of the two forces. Which force is dominant in that direction the object will go. That's there. Okay, and first law, the complete description. And here this picture is when object is released, then there will be inertia of motion. As a result, at the lowest position the object will not stop, it will rise to a certain height. And this picture tells that if you have released a ball and you have inclinations at different steepness or at different angles with respect to the horizon, then this object on the other inclined plane also will rise to exactly the same height. That is by Newton's first law of motion. And this is about inertia. This is that caroms board where with the striker you hit a stack of coins. Only the bottom coin flies and remaining stack of coins will fall on the table. This is due to the inertia of rest of the remaining coins. Force is only applied to the bottom coin by the striker. So the bottom coin flies and remaining all has the inertia of rest, so they will fall down. That's what there. You have to, when you read the whole thing, that's what will be found. This is another example of inertia of rest. Here on the tumbler, a card is placed and on the card a coin is placed. The card is given a flickering force, like with the finger it is flickered. So the card flies and this coin, no direct force is applied. So that has the inertia of rest, and that coin, in the next picture you see the coin falls down because of inertia of rest of the coin. And here in this next paragraph it is written inertia, relation between inertia and mass. We always remember that heavier and more mass objects offer large inertia, means more inertia, more inability if the object is having more mass. So quantitatively, inertia of an object is measured by its mass. So here the last paragraph is kind of definition of inertia. Inertia is the natural tendency of an object to resist a change in the state of motion or of rest. The mass of an object is the measure of inertia. So these all we discussed in this notes. Okay. Now come to Newton's second law of motion. Newton's second law of motion. So here this complete literature on the theory part, and here the derivation, those all, which I wrote in a very simple way here. So Newton's second law of motion states that Newton's first law of motion was, when no force is applied, what happens? An object at rest remains at rest. An object in uniform motion continues to travel with the same speed. Newton's second law of motion states that what will happen to a body if force is applied. So that's Newton's second law of motion. So statement says that when force is applied to a body, the body either accelerates or decelerates. The acceleration or deceleration thus produced in the body is directly proportional to the applied force and inversely proportional to the mass of the body. So this is the statement of Newton's second law. If force is applied, the body will either accelerate or decelerate. But acceleration or deceleration will depend upon two factors. One is force, another is mass. Acceleration will be directly proportional to force. Directly proportional meaning is, if more force is applied, more acceleration will be seen in the body. If less force is applied, less acceleration will be seen in the body. And similarly, acceleration and mass of the body are inversely related. Means if mass of the body is more, then acceleration produced in that mass will be less. And if mass is less, then acceleration produced in that body is more. That means lighter objects travel with greater speed on application of a simple force. But the same force applied to a large mass, much acceleration or much speed cannot be seen in that object. So here these two are the relation that we get by Newton's second law of motion. When we club it, this we write only once, but F and 1 by m we multiply. So acceleration proportional to F by m, then we go for a cross multiplication. Then we will get force proportional to mass into acceleration. And whenever we remove the proportionality symbol, we will get is equal to and a proportionality constant. In Newton's second law of motion, proportionality constant is 1. So ultimately we will get force is equal to mass into acceleration. Force is equal to mass into acceleration is the first mathematical expression of Newton's second law of motion. But Newton's second law of motion can also be mathematically expressed in another way. Since we know that force is mass into acceleration, and acceleration is the rate of change in velocity. V is final velocity, U is initial velocity, and then we distribute mass over this bracket. We get force as mass into final velocity minus mass into initial velocity. Also we know that mass into final velocity is final momentum, and mass into initial velocity is initial momentum. So here we write final momentum, here we write initial momentum. Force is the change in momentum by time, means rate of change in momentum. Final momentum minus initial momentum is change in momentum, which we will represent by delta P. So force is the rate. Rate means with respect to time. Force is rate of a change in momentum. So this is the second formula for force by Newton's second law of motion. So mathematical formulas for force by Newton's second law of motion is F is equal to ma and F is equal to rate of change in momentum. That was Newton's second law. Now this is an important part of this chapter. How we derive Newton's first law's mathematical expression from Newton's second law's mathematical expression. So deriving Newton's first law from Newton's second law. Newton's second law is force is the rate of change in momentum. That's by second law. So first law states that if no force is applied, so if we make force a 0, then cross multiply 0 into t is a 0. 0 is mv minus mu. You transpose mu to the other side, that becomes plus mu. Mu is mv, mass you cancel. You will get initial velocity is equal to final velocity. And this is what is Newton's first law. When no force is applied, initial state of the body will be equal to final state of the body. Next, we will find the relation between SI unit of force, that is Newton, and CGS unit of force. Since we know that force is mass into acceleration, SI unit of force is Newton. So how do you understand Newton in simple terms? So 1 Newton is 1 kilogram meter per second square. So this is it. And in CGS unit, force is measured in terms of dynes. So how do you understand force in CGS unit? So if force is in terms of dynes, then mass should be in terms of grams and acceleration should be in terms of centimeter per second square. So 1 dyne is 1 gram centimeter per second square. Now we know Newton is what, dyne is what. So we'll see how are Newton and dyne related. So we start here. 1 Newton is 1 kilogram meter per second square. 1 kilogram is 1000 grams. 1 meter is 100 centimeter. And we know that 1 gram centimeter per second square, 1 gram centimeter per second square is 1 dyne. So here 1 beside 1, 2, 3, 4, 5, 10 to the power 5. So 1 beside 5 zeros. So 10 to the power 5 gram centimeter per second square, which is 10 to the power 5 dynes. So ultimately 10 to the power 5 dynes make a Newton. So that's a relation between SI unit of force and CGS unit of force. You remember this is a 1 mark question. Then coming to impulsive force or impulse and impulsive force. Like how do you understand this? Like what is the meaning of friction? Friction is an opposite direction force or an opposing force. Thrust is a force that acts on a body in a direction perpendicular to the surface. Similarly, impulsive force is also a particular kind of force. What kind of force? It is actually a force that is always maximum in quantity but acts on a body for an instant of time. So whichever force, whenever a maximum force acts on a body for an instant of time, that kind of forces are called impulsive force. That is, in a pulse, that force is applied. Let's see the definition. Impulsive force is represented by this symbol. How do you write this symbol? You write like this. And this is called TOU, kind of Greek alphabet. So impulsive force represented by or notation tau. Definition, it is the maximum force. So what is impulsive force? Remember to tell that it is the maximum force that acts on a body for an instant of time that brings about change in momentum of the body. So remember this definition. Impulsive force is the maximum force that acts on any body for an instant of time. And if it happens, then what happens to the body? The body undergoes a change in momentum. That's what impulsive force is. Now by Newton's second law of motion, F is equal to ma. Acceleration is a rate of change in velocity. So when you multiply m or distribute m over the bracket, you get something like this. This is a second mathematical expression of Newton's second law of motion. So here we just go for a simple cross multiplication, and then we will get force into time is change in momentum. Force into time is actually impulsive force. Means this force will be called impulsive force when time is just a moment. So maximum force that acts on a body for an instant of time, and that results in, means is equal to, results in a change in momentum of that body. So here change in momentum, if you put aside, you will know that impulsive force and time of impact are inversely related. That means if time of impact is less, force is maximum, and time of impact is more, then force is less. So impulsive force is inversely proportional to time of impact. Keep this in mind where to use this concept. Like I hope I have written examples for this. Yes, I have written. So mathematical expression for impulsive force is force into time is change in momentum. Force is maximum force when time is instant of time. SI unit of impulsive force. SI unit of impulsive force is Newton second. So this is actually impulsive force. Impulsive force is not just force, it is force into time. So impulsive force is measured in terms of Newton second, and since this is equal to change in momentum, so impulsive force can also be measured in terms of unit of momentum, that is kilogram meter per second. Now how to understand that? Sometimes in this chapter we will be asked questions like why it hurts when we jump on concrete and it doesn't hurt when we jump on a cushion. So keep this in mind. When you jump on a concrete, time of impact is very less. And we know that force, impulsive force and time of impact are inversely proportional. So if time of impact is less, impulsive force is maximum, so maximum hurt. But when we jump on cushion, when somebody jumps on cushion, time of impact is more. That means from the surface of cushion, when we jump on the surface, we go deep down, sailing through the cushion. That means we take more time. Time of impact is more, so impulsive force is less. That's why in Olympics events, the pole event, jumping from the pole, they jump on the cushion, so that time of impact is more and impulsive force is less, and the person is less hurt. So that is what is written in this paragraph. Now we almost have come to the last but one topic of this chapter, theory concept part. This is Newton's third law of motion. Newton's third law of motion is very popular one. For every action, there is an equal and opposite reaction. Mathematically, we'll write FAB is minus of FBA. Means force exerted or force applied by body A on body B is equal and opposite to force applied or exerted by body B on body A. So that's how we have to read Newton's third law of motion. Now, talking about some examples of Newton's third law of motion, be very careful when you choose examples for Newton's third law of motion, because in this example, one object does action and other object gets a reaction. So action and reaction both should not occur to the same object, and if it occurs, that is not the example of Newton's third law. So best example is a man jumping from a boat. So man moving forward, so action, and boat moving backward, that is a reaction. So that's the best example. And shooting of a bullet from a rifle or a gun is also a good example of Newton's third law, because bullet moving forward is action. Bullet moving forward is action, and the gun or the pistol or rifle getting a recoil is a reaction. So one did action and other got reaction. Such should be the examples of Newton's third law of motion. Now again, coming back to the textbook from our discussion part. So this is a nice picture. What you understand out of this picture? So here this person catches or takes a catch of the cricket ball, the fielder. So this ball is coming with high momentum, and if this fielder holds the ball all of a sudden, then the momentum of the ball all of a sudden turns zero. So vast high momentum to zero momentum means this ball underwent vast change in momentum in just an instant of time. So definitely force that acted on the palms of this person or fielder is maximum, and that will hurt the palm of this fielder. That's the reason that when fielders take a catch, they don't all of a sudden stop the ball. They hold the ball and drag their hand backward. And in this process, the time of impact is increased. And we know that force and time of impact are inversely related. So if time of impact is more, force is less. So when the cricketer or fielder pulls the hand backward, time of impact is more. So force or impulsive force that acts on the palms is very little. As a result, it doesn't hurt the palm. So this is the picture for impulsive force. Then we have few examples that we'll try to discuss. And then Newton's third law, the best example is the man jumping from boat, the forward force of the bullet and recoil of gun, that's fine. But when Newton's third law of motion experiment is done in the laboratory, it is done using two spring balances. One spring balance is connected to a wall and another spring balance is hooked to the previous spring balance, and with hand force is applied. So when we pull this spring balance, we are doing action. As a result, this spring balance gives some reading here. We read here how many newtons of force is applied by pulling. When we pull this, this spring balance is being pulled by this wall. So we will see the same reading in the other spring balance. So the reading that we see in this spring balance is action, and the reading that we see in spring balance B will be the reaction. So action will be equal to reaction. So forward force and backward force will be equal in magnitude, and then Newton's third law of motion is verified through this activity. Now we come to the law of conservation of momentum. So this travels all the way, kind of definition and derivation, a bit complex, which I made it very simple here. What is the law of conservation of momentum? Law of conservation of momentum has a statement. We understand the statement first. It states that in an elastic collision, elastic collision means during a collision, the colliding object's forces only work and no external force acts in that case. So in an elastic collision means when no external force is applied, external unbalanced force is applied. So in an elastic collision of two or more bodies, the sum total of momenta of the bodies before collision is the same as the sum total of momenta of the two bodies or two or more bodies after collision. Or in short, we can say that in an elastic collision, the total momentum of the objects under collision is conserved. Mathematically, mu plus mu is mv plus mv. This is object A, object B. This is object A, object B. So initial momentum of object A plus initial momentum of object B is equal to final momentum of object A plus final momentum of object B. Let us derive this. So for the derivation or the proof, let us prove this. For the proof, assume that these are two objects of different masses, m subscript A, m subscript B, with initial velocity UA, initial velocity UB. So these two, either they are traveling in same direction or opposite direction with different speeds. Ultimately they collide each other. When they collide, after colliding their masses will be same, but velocities will change. So VA is final velocity of this and VB is final velocity of this. So let MA, MB be the masses of the two bodies. UA, UB, VA, VB are their initial and final velocities. Now let's begin. Since these two objects collided, force applied by A on B is equal and opposite to force applied by B on A. So this is by Newton's third law of motion. By Newton's second law of motion, we can write force is mass into acceleration, mass into acceleration. So this is the left side is about object A and right side is about object B, but the negative sign is there. In place of acceleration, we'll write rate of change in momentum. In place of acceleration here also we'll write that. So this is all about object A, all about object B. Here, time of impact, we will not write T subscript A or T subscript B, because when two objects collide, they collide at a common time. So time is common. So in the next step, we will cancel them. And then m subscript A, we will distribute over this bracket, and negative m subscript B, we distribute over this bracket, and we get expression like this. After this, these two negative terms we will transpose to the other side and they will become positive, and then ultimately we will get sum total of momentums of the two bodies after collision is equal to sum total of momentums of the two bodies before collision. Hence, law of conservation of momentum is proved. So this is the law of conservation of momentum statement, mathematical expression, and you have seen how the derivation is done. This is the last theory or concept part of the chapter. Then we come to the NCERT textbook exercise question. The first question, I'll read it from the textbook itself. The first question states that an object experiences a net zero external unbalanced force, means the body is under no external force. So it's like it experiences a net zero external unbalanced force. So there is no outside force that is acting on the body. is it possible for the object to be traveling with a non-zero velocity? So the question says, if the object is under no external force, is it still possible for the object to be traveling with some velocity? If yes, state the conditions that must be placed on the magnitude and direction of velocity. If no, we have to give a reason. So the answer is yes, it is possible for the object to be traveling with a non-zero velocity. Means if there is no external force applied on the body, still the body can have some velocity. So yes, it is possible for the object to be traveling with non-zero velocity in the absence of external unbalanced force. The necessary conditions are: the object should be already moving with some uniform speed along the straight line first. That means if the object is already moving, it will have the same velocity when there is no external unbalanced force. Second point, there should be no change in the magnitude of speed or velocity and the direction of motion. Next, there should be no air resistance and there should be no friction between the object and the surface in contact. If any of the above conditions are not met, then the answer is no. This is because external unbalanced force is needed for initiating motion and for any subsequent change in its velocity. That's the answer to the first question. Now the second question is, when a carpet is beaten with a stick, the dust comes out of it. Give a reason to that. So this is related to the inertia of rest. How to answer this? Dust particles in the carpet tend to remain at rest due to inertia of rest. That is why the particles fall down. See, very simple. If a carpet is beaten, then forces are directly applied to the carpet. No direct force is applied to the dust. So the dust particles stay at rest. And since the carpet recedes or moves back, the dust particles, since they have no surface to stand, they fall down. In that way, the dust particles get detached from the carpet. The third question, why is it advised to tie any luggage kept on the roof of a bus with a rope? It is due to inertia of the luggage. That means if the luggage is not tied, when the vehicle all of a sudden starts, the luggage may fall backward, or when the brakes are all of a sudden applied, the luggage may fall forward, or the luggage may be thrown out of the center of curved track if the vehicle takes a turn, in case the luggage is not tied. So that's the answer. We can write the answer in short as, this is because when bus starts suddenly or stops suddenly, the luggage may fall due to inertia of the luggage. The luggage or the bags, those all have the inability to change itself their state of rest, uniform motion or direction. The fourth question, a batsman hits a cricket ball which then rolls on a ground or level ground. After covering a short distance, the ball comes to rest. The ball slows to stop because you can make out that when the ball is rolled on the ground, the ball stops after some time. It is due to friction between the ball and the ground. So we have to choose one among them. So the first one, does the batsman, it is because the batsman did not hit the ball hard enough? No, that's not the case. Velocity is proportional to force exerted on the ball. That's also not the case. The third one, there is a force on the ball opposing the motion. So this is the reason why the ball subsequently stops. The last reason I need not read because this is a single choice correct answer. Then we have a numerical problem. The numerical problem is, a truck starts from rest and rolls down a hill with a constant acceleration. It travels a distance of 400 meters in 20 seconds. Find its acceleration and force acting on it if its mass is 7 tons. They wrote 1 ton is 1000 kilograms. Let's solve this question. So I have already written the question and left space for solving. So hope this part of the paper is visible in the camera. Yeah, it is visible. So our truck starts from rest. So what is given to us? Initial velocity of the truck is 0. rolls down the hill at constant acceleration. It travels a distance of 400 meters. So distance traveled is 400 meters in a duration of 20 seconds. 20 seconds is written, 400 meter. We are supposed to find acceleration. Next, we have to find force acting on the on it if mass. So we are given mass as 7 metric tons. 1 metric ton is actually 1 ton is 1000 kilograms. So in the textbook 7 tons. So 1 ton is 1000 kilograms. Let's begin. First we'll find acceleration. So from these 4 information we have to find acceleration. Let's go for the second equation of motion, that is S is ut plus a half at square. So we know this, that this is 400 meters. Initial velocity is 0, so 0 times anything is 0, that we can forget. So here half. Acceleration is our requirement, t square means a 20 square. So acceleration is, just go for a cross multiplication, 2 times 400 divided by 20 square is of course 400. You cancel this. So acceleration is a 2. Acceleration is a 2 meter per second square. Now we are supposed to find force. By Newton's second law of motion, we know that F is ma, mass is 7000 kilograms, and acceleration is 2 meter per second square. 7 2 is 14, so it is 14,000. 1 kilogram meter per second square is a Newton. So force applied is 14,000 Newton. The sixth question says, a stone of 1 kilogram is thrown with a velocity of 20 meter per second across a frozen surface of a lake, and that comes to rest after traveling a distance of 50 meters. We are supposed to find force of friction between the stone and ice. So the question I have written ahead of time. Now I'll just pick up the information. Mass of stone is 1 kilograms. Is thrown with a velocity. So initial velocity of throw is 20 meter per second, and ultimately that stone comes to rest. So final velocity of the stone is 0 after traveling a distance of 50 meters. You see, everything is in MK system. We are supposed to find force of friction. Fine. Force is mass into acceleration. So mass is given. Acceleration we should find. So acceleration is our requirement. Now initial velocity, final velocity, displacement and acceleration, they are in the third equation of motion. So we'll apply v square minus u square is 2as, and this is 0 square minus 20 square means what, 400 is twice. Acceleration is our requirement and displacement is 50. So fine. So this is negative 400 upon 2 times 50 is 100, and we get acceleration as negative. That means the stone decelerates with 4 meter per second square. So therefore by Newton's second law of motion, F is ma. So mass times acceleration, mass is 1 kilograms and acceleration is negative 4 meter per second square. So 1 into minus 4 is minus 4. Kilogram meter per second square is a Newton. So the force of friction is 4 Newton. Either we conclude like this, or we should say that a force of 4 Newton is applied or exerted or found in a negative direction. Now coming to 7th question. 7th question states, a 8,000 kilogram engine pulls a train of 5 wagons, each of 2,000 kilograms along the horizontal track. If engine exerts a force of 40,000 Newton and track offers a friction of 5,000 Newtons, we have to calculate two things: a net accelerating force, not acceleration. It's a net accelerating force. Second, acceleration of train. So that's a question that is written here, and we can solve it in this space. So all the things that is given to us, I'm just having a collection of details. So what is the mass of engine? Mass of engine is 8,000 kilograms. So once let me check whether this space is visible in the camera or not. Yes, it is. Mass of engine is this, that pulls a train of 5 wagons. So mass of engine is this, mass of train. train is made up of 5 wagons and each wagon is of mass 2000 kilograms. So mass of train is 10,000 kilograms. Then engine exerts a force. So force exerted by engine is 40,000 newtons. And track offers a friction. So force of friction is 5,000. So we have to write it as negative 5,000 newtons. With this information, we have to find first net accelerating force. So net force. Net force is the total force that you see, force due to engine plus force due to friction. Force due to engine is 40,000 Newton plus friction. Friction is in opposite direction, so we have a negative sign. So net accelerating force is 35,000 newtons. And next, what is acceleration of train, not engine? So we know that by Newton's second law, acceleration is force by mass. So acceleration of train is the net force by mass of train. Net force is 35,000 newtons and mass of train is 10,000 kilograms. Newton per kilogram is meter per second square. So acceleration of the train is 35 by 10 means 3.5 meter per second square. Then the next question is an automobile vehicle has a mass of 1500 kilogram. What must be the force between vehicle and road if a vehicle is to be stopped with a negative acceleration of this? Mass is given, acceleration is given. They are asking us force, so it's directly Newton's second law of motion. So F is ma. Mass is 1500 kilograms. And there is a negative acceleration. So we'll write here negative acceleration of 1.7 meter per second square. So negative sign stays just to tell that it's a force that is used to stop a moving vehicle. So 15 times 17 we should do. So this turns out to be 255 and there are 2 more zeros and decimal from back. So force of 2,550 newtons in opposite direction. Then the ninth question is an MCQ question. So keep this in mind, these questions answers I have taken from the previous book, not from the rationalized syllabus, because rationalized syllabus content is so much cut short that sincerely we are not learning anything in fact. So I have taken this from the previous textbook where information is good. So ninth question, what is the momentum of an object of mass m moving with velocity v? Momentum is actually mass into linear velocity, so this is the option. We need not see any of them. Now coming to 10th question. 10th question from the textbook, let me read first. Using a horizontal force of 200 newtons, we intend to move a wooden cabinet across a floor at a constant velocity. So applied force is 200 newton. With this we want to move an object on the table. The question is, what is the friction or frictional force that will be exerted on the cabinet? If applied force is 200 newtons, then force of friction will be equal in magnitude to the applied force but opposite in direction. So minus 200 newton, negative 200 newton. 11th question, two objects each of mass 1.5 kilograms are moving in the same straight line but in opposite directions. Okay, good. Velocity of each object is 2.5 meter per second before collision, during which they stick together. Oh fine, I understand that. There are two objects of this much mass. They are moving in a straight line but in opposite direction with a velocity of 2.5 meter per second, and they ultimately collide, and after collision they stick to each other. they get attached to each other. The question is, what will be the velocity of combined object after collision? So this is an application of law of conservation of momentum. So there are two objects. So I am writing for object 1 mass m1, which is 1.5 kilograms, and object 2 has a mass of same, because both the objects have same mass and both of them have the same velocity but opposite direction. So one of them is 2.5 meter per second and another is a negative of 2.5 meter per second, and they collide, it seems, and after collision they stick to each other. And if they stick to each other, then final velocity of the first object should be equal to final velocity of second object, and that is the common final velocity which we are supposed to find. What will be the velocity of a combined object after collision? So we are applying the law of conservation of momentum. So let's write the statement first. By the law of conservation of momentum. By law of conservation of momentum. Law of conservation of momentum's mathematical expression is mu plus mu is mv plus mv. So first object, second object, first object, second object. Let's input all the values here. 1.5 times 2.5 plus 1.5 times negative 2.5. The right side, V1 is V, V2 is also V. So highest common factor is the combined velocity. M1 plus M2 will go in the bracket, which is 1.5 plus 1.5. So here you see the same number, negative of same number. So left side turns 0, right side is V times 3. So final velocity is 0 upon 3, which is 0. That means when these two objects collide with each other and stick to each other, finally they stop, they don't move. Now the 12th question, the question states, according to the third law of motion, when we push an object, the object pushes back on us with equal and opposite force. If object is a massive truck parked along roadside, it will probably not move. That means if you try to push a truck, will it move? Of course it will not move. That is what is being said in the question. A student justifies this by answering that two opposite and equal forces cancel each other. Comment on this logic and explain why truck does not move. So the student says that the force that we apply on the truck also applies equal force on us. So by Newton's third law, they cancel each other. Ultimately, truck doesn't move. Let's see what justification we can give. So what the student said, that justification is not true, because if truck doesn't move, it doesn't mean that we have applied the same force that the truck is applying on us. It's not true. There should be correct amount of force to make or to overcome the force of friction between the truck and the surface on which the truck is placed. So justification given by the student is not correct. This is because forces of action and reaction never act on one body. That means we are only pushing the truck and we are only expecting reaction. That's not possible. So there is no question on cancellation. The truck does not move because the push applied is far less than the force of friction between the truck and the road. This is very important. That means applied force should be a bit more than the force of friction between the object and the surface on which the object is placed. That is a limiting friction. That much frictional force if we apply, then the object just moves. We also do not move. So that's about the truck. Why the person who is pushing the truck, that person doesn't move. That means we also does not move because force of reaction acting on us is less than the force of friction between us and the road. So that's a justification about it. Now coming to 13th question, which is a numerical problem. I'm reading the question here, I'll solve in the paper. The question is, a hockey ball of mass 200 grams traveling at 10 meter per second is struck by a hockey stick so as to return it along its original path with a velocity of 5 meter per second. Calculate magnitude of change in momentum occurred in the motion of the hockey ball by the applied force. So the information is I just put this information in form of a diagram. They say there is a hockey ball. This hockey ball has a mass of 200 grams and that is traveling with a velocity of 10 meter per second. See, MK system. So convert gram to kilogram by dividing by 1000. So 200 divided by 1000. So that turns out to be 0.2 kilograms. So this ball is moving forward, and then when it reaches a particular location, that is hit by a hockey stick. So this is the hockey stick with which it is hit. As a result, this ball returns along its original path with a velocity of 5 meter per second in opposite direction. That's why we have to take care of the sign convention. Now with this information, we have to calculate change in momentum. So how do you calculate the change in momentum? Change in momentum is del P, which is final momentum minus initial momentum. Final momentum is mass into final velocity. Initial momentum is mass into initial velocity. Take highest common factor mass. Then we have V minus U. Mass is 0.2 kilograms. Final velocity is -5 minus of initial velocity 10. So we have 0.2. This is -15. So 2 15s is 30, and where the decimal should be placed after one digit from right side and the negative sign. So change in momentum is -3 kilograms meter per second. So that's the 13th question. Now the 14th question, a bullet of mass at 10 grams traveling horizontally with a velocity of 150 meter per second strikes a stationary wooden block and comes to rest in 0.03 seconds. We are supposed to calculate distance of penetration of bullet into the block and also calculate magnitude of force exerted by the wooden block on the bullet. So the given information, I will present it in form of a diagram. So there is a wooden block and there is a bullet. So this is that bullet. Okay. So according to the question, mass of the bullet. So mass of the bullet is at 10 grams. If it is 10 grams, divide by 1000 to get it in terms of kilograms. So mass of the bullet is 0.01 kilogram. We should work in either MK system or CJ system. So it is traveling with an initial velocity of 150 meter per second. So U subscript B is initial velocity of bullet, which is this. And this comes to rest. This bullet finally comes to rest. So final velocity is 0 in a time duration of 0.03 seconds. When it comes to rest, when it hits the block, and in the question they say that this gets embedded inside. So we have to calculate the distance of penetration. That means at this location it had this 150 meter per second, and as it went inside, finally at this location final velocity turned 0. So we have to calculate a distance of penetration of the bullet into the block. It is bullet, B-U-L-L-E-T. Okay. And also we have to calculate magnitude of force exerted by the block on the bullet. So first distance of penetration. So S is our requirement. So what we do is, first let's calculate the acceleration or deceleration produced in the bullet using this much information. Acceleration is V minus U by T. So this is 0 minus 150 by 0.03 seconds, which is negative 150. This denominator contributes 2 zeros upon 3. So acceleration is negative of 3 5s 15. So negative 5000 meter per second square. So we got acceleration. Fine. Now we want distance of penetration. So let's go for third equation of motion. V square minus U square is 2AS. So 0 minus 150 square is twice of negative 5000. S is our requirement. Negative of 15 square is 225. 0 upon the negative sign comes here. 2 5s 10 and the remaining 3 zeros is the distance of penetration. So denominator 2 zeros, numerator 225. So distance of penetration is 2.25 meters. This is the first bit that they asked in the question. Next we have to calculate the force exerted by wooden block on the bullet. Force is mass into acceleration. Mass of the bullet is 0.01 kilograms and acceleration is negative 5000 meter per second square. So 5 into 1 is 5, of course. Put all the 3 zeros and decimal shift to place. Kilograms meter per second square. 1 kilogram meter per second square is a Newton. So, and the negative sign is also there. So negative 50 newtons. So the wooden block applies or exerts a force of 50 newtons in opposite direction, means to stop the bullet. The 15th question, an object of mass 1 kilogram traveling in a straight line with a velocity of 10 meter per second collides with and sticks to a stationary wooden block of mass 5 kilograms. Fine. So an object of mass 1 kilogram collides with a wooden block and ultimately sticks to it. Then they both move off together in a same straight line. We are supposed to calculate total momentum just before the impact and just after the impact, and also we have to calculate the velocity of the combined object. So the same question I wrote here first. Now I'll write the details. So mass of object is 1 kilograms. That is traveling a straight line with a velocity. So initial velocity of the object, O for object, 10 meter per second, that collides and sticks with a stationary wooden block. So wooden block is a stationary initially, so 0, and mass of wooden block is 5 kilograms. And after collision, the object sticks to the wooden block and both of them move with a common velocity. So final velocity of object is equal to final velocity of wooden block, and both of them have a final common velocity. That is what we are supposed to find. Here we have to find 3 things. First thing is total momentum, impact. So before the object and the wooden block collides, means what? Momentum before, mass into initial velocity of the object, and momentum before of the wooden block. That means mass of wooden block, initial velocity of the wooden block. So we know that mass of object is 1, initial velocity is at 10, mass of wooden block is 5, but it was at rest. 5 into 0 is 0. So total momentum of the object and the wooden block before collision is 1 into 10, that is at 10 kilograms meter per second. Then we have to find total momentum just after impact. Keep this in mind. For this we have nothing to calculate, because by the law of conservation of momentum, sum total of momentums of two objects before collision is the same as sum total of momentums of the two objects after collision. So this is initial momentum of the object, initial momentum of the wood, final momentum of object and final momentum of the wood. So initially whatever was the sum total of the momentum, finally also it is the same. So 10 kilograms meter per second. Then we have to find their combined velocity. So we know that sum total of momentums of the two body before collision was at 10. And here final velocity of object is a v, final velocity of wooden block is also v. So highest common factor is v, mass of object plus mass of wooden block goes into the bracket. So this is 1 and this is 5. 1 plus 5 is 6. So final common velocity is a 10 by 6. So 2 5s, 2 3s. So v is final velocity is 5 by 3 meter per second. We can convert this to decimal also. The 16th question, an object of mass 100 kilograms is accelerated uniformly from velocity of 5 meter per second to 8 meter per second in 6 seconds. So we are given mass, initial velocity, final velocity and time. We are supposed to calculate initial and final momentum and magnitude of force exerted on the object. Very simple question in fact. Mass is 100 kilograms. Fine. So mass is 100. Actually there are some number variation between this textbook which has got more information because it is a year old. The latest rationalized syllabus, number of questions are less and some number variation. I remember that this is some 10 kilograms in the rationalized syllabus book. So I am answering based on the question that is there in this book. So information sake, this is good. So mass is this. Initial velocity is 5 meter per second. Final velocity is 8 meter per second. Time is 6 seconds. What are they asking us? First, initial momentum. Initial momentum is mass into initial velocity, that is 100 times 5. Oh no, in that case this question mass is 100. Fine. So 500 kilograms meter per second. Second, the question is what is final momentum? Final momentum is mass into final velocity, that is 100 kilograms times 8. So 800 kilograms meter per second. And ultimately they are asking us what is the magnitude of force. By Newton's second law of motion, we know that force is the rate of a change in momentum. So 800 minus 500 upon 6. So this turns out to be 300 by 6, 6 ones, 6 fives 30. So force is 50 newtons. So that's the 16th question. 17th question is a theoretical question. I just read out. It's a good one. Concept understanding sake, this is good. Akhtar, Kiran and Rahul were riding a motor car that was moving with a high velocity on the expressway when an insect hit the windshield and got stuck on the windshield. Akhtar and Kiran started pondering over the situation. Kiran suggested that insect suffered a greater change in momentum as compared to change in momentum of the motor car. And Akhtar said that since motor car was moving with larger velocity, it exerts larger force on the insect. And as a result, insect died. So ultimately the situation is, Kiran says that because insect all of a sudden dashed on the windscreen of the car, insect underwent vast change in momentum. Of course it is true. And Akhtar says that the motor car is moving with larger velocity, so it has exerted greater force on the insect, due to which the insect died. That is also in a way true, but not complete explanation in fact. Then Rahul, the third person, while putting on entirely new explanation, said that the motor car and the insect experienced the same force and a change in their momentum. Comment on this suggestion. In fact, Rahul's justification is more correct by Newton's third law of motion. If an insect hits the motor car, the insect as well as the motor car experience equal magnitude of force but in opposite direction. And of course both of them, the insect as well as the vehicle, undergo a change in momentum. Now the last question, how much momentum will a dumbbell of mass at 10 kilogram transfer to the floor if it falls from a height of 80 centimeter? Downward is acceleration due to gravity. So I have not written the question, but I'll pick up information from the question. So the question is this. Let's note down what we are supposed to find. Dumbbell transfers to the ground. Momentum, see, if dumbbell is dropped from a certain height, it will have the maximum momentum just before hitting the ground. So how much momentum it will have finally, that much momentum it will transfer to the ground. So we have to calculate final momentum. So final momentum is actually mass into final velocity. Now let's see what is given in the question. So we are told that mass is a 10 kilograms. Well, that's good. And the dumbbell is dropped. So initial velocity is 0. It is dropped to a height of 80 centimeter. Divide 80 centimeter by 100 and we'll get the answer in meters. So 0.8 meters. Acceleration is in vertical direction. So we will not write A. A is for linear acceleration. Vertical acceleration is a G. This is called acceleration due to gravity, which is 10 meter per second square. So mass is known. We want only final velocity. So let's apply these three to find the final velocity. So we will apply the third equation of motion. V square minus U square is a 2gs. So final velocity with which the dumbbell hits the ground, that we are supposed to find, which is twice into 10 into 0.8. So V square is 10 and 0.8, the decimal cancel. So we have 2 into 8, that is 16. Final velocity is a plus or minus under radical 16, which is plus or minus 4. So here velocity is in correct direction. So velocity is a positive 4. So final velocity with which the dumbbell hits the ground is 4 meter per second. So the momentum transferred to the ground is the final momentum, which is mass into final velocity. Mass into final velocity is a 10 into 4, which is 40 kilograms meter per second. So this completes the textbook exercise questions, and then there are good number of in between in text blue questions that I will answer in the next part of the video.